Models of the atom. We first started off at the beginning of this unit with the Dalton model of the atom, which, of course, we know is the solid sphere model of the atom. It's the marble model of the atom, right? The atom is a tiny little marble. All the marbles are different. All the atoms are different, but you don't get any smaller. Okay, the marble is the marble. The atom is the atom. Then we went to 1897 and Thomson's model of the atom. Sometimes they call it the plum pudding model of the atom because it says that there's a whole bunch of little electrons floating around in a sea of positive charge. Kind of looks like plum pudding or chocolate chip cookies. Okay, a bunch of little chocolate chips floating around in a sea of cookie dough or the sea of positive charge. That's a big deal. Yeah, that was a big, big deal, Thomson's model of the atom, because it was the first model that acknowledged or at least proved that there was something smaller than the atom, that there's something inside that little marble or little who's moving around inside this speck of dust. And then we went yesterday to the Rutherford model of the atom. The Rutherford model of the atom, by the way, we also call sometimes the planetary model of the atom. And as we go through these various aspects, observations, and conclusions that we drew from these observations, it'll become pretty clear why we sometimes call it the planetary model of the atom. Let's describe right now, though, the experiment that Rutherford used in order to come up with his planetary or Rutherford model of the atom. It consisted of basically a little box here. This little box has not alpha particles in it, but some kind of radioactive material in it. I don't remember what it was. Okay, I'm sure it was a very specific, defined radioactive source. I just don't remember what that was. It doesn't matter. It produces alpha particles. It decays into alpha particles. Those alpha particles leave the little hole in this box, and they go towards this thin layer of gold foil. And then they do something when they hit that gold foil. Maybe they go through it. Maybe they bounce back. Whatever. They do something when they hit that gold foil. We want to know what that something is. We want to know whether they go through it or bounce back or whatever the case may be. So we put a screen all around it. We call it a scintillation screen. It glows when it's hit by alpha particles. So that helps us to determine exactly where these alpha particles hit. Rutherford and his assistants, Geiger and Marsden, observed three things. They observed that most of the alpha particles did what? Most of these little alpha particles fired one by one at this gold foil did what? Most of them went straight through, yeah. Okay, most of the alpha particles just went straight through, which is exactly what we predict, right? Most of them go straight through. But some of these alpha particles didn't go straight through. Some of these alpha particles did what? Certainly a minority, a significant minority of these alpha particles, but a measurable number, a noticeable number of them, they were deflected. So when they hit this gold foil, they go through, but they're deflected down like this, or they're deflected like this. So we'll say some alpha particles deflected. How much did they deflect? Well, depends on how close to the nucleus they got. Remember that when Rutherford did this experiment, he didn't know about the structure of the atom. He didn't know that there was a small, dense, positively charged nucleus in the middle. But in the end, the results still had to agree with that reality that there is a small, dense, positively charged nucleus. Let's make this gold foil a little bit bigger for a second, okay? And we're blowing it up. We're magnifying this gold foil. Inside this thin layer of gold foil is a nucleus right there, and that's that positively charged nucleus. Remember, Rutherford doesn't know this yet. You got an alpha particle that's coming towards that nucleus, at least more or less toward that nucleus. Oh, look, it's positive. It's going to be repelled by the nucleus, so it's going to go down here. You got another alpha particle that's going here. Oh, it's going to be repelled by the nucleus as well, so it's going to go up here. What about another one right here? Where's it going to go? It's going to be repelled as well. Repelled more or less? Joey? More, because it's closer, right? If the distance is smaller, then it's going to be repelled more. This guy, funny enough, is going to go down here, right? The guy that ends up being closer to the nucleus is going to be repelled more, and it's a bigger scattering of it. Right? Some of these alpha particles are deflected. A few of these alpha particles now, not very many, But a few of these alpha particles did what? Okay? They bounce back. So some of these alpha particles, a few of them will go back like this. It's kind of like the alpha particle going in like this and getting so close to this, but wait a second, it's such a massive force of repulsion. What happens to it? It goes back. Maybe straight back, maybe back at an angle like this. Bottom line is it goes back. Now, the fact that most of these alpha particles went straight through, what did that tell us? What did Rutherford and his assistants learn from this observation? Remember the analogy we used yesterday? Guys running across the football field? What do we learn when 100 of those 110 people ran straight across the football field? Good. Most of it's empty space. Not all of it, because not all of the particles went straight through, but most of the atom is empty space. Some of the alpha particles are minority, but still a significant number of them were deflected. What did that tell us? Look at the picture over here. There had to be something positive repelling it. It had to be small, because most of the atom is empty space. We had a small positive nucleus in the middle. And a few of the alpha particles bounce back. What did that tell us? Well, if they bounce back, yeah, it's got to be dense. It's got to be heavy. The nucleus is heavy, right? Remember the analogy yesterday. If you got a 2-year-old sitting in the middle of the football field, and James, you're running across that football field, and you run into the 2-year-old, then you're just going to plow right through them, right? If you got a 300-pound offensive lineman in the middle of the football field, and you run into him, you're going to bounce right off of him and bounce back, right? So it tells you that there's something small, relatively speaking, not that the 300-pound offensive lineman is small, but relative to the football field, he's small. Okay? He's heavy. He may even be dense. I'm not sure. Okay? Bottom line is he's got to be small. He's got to be positively charged. He's got to be heavy. Otherwise, you're not going to bounce off. Good? So what does that lead us to? Where's the end in this? What's the goal in this? Well, ultimately, we want to come up with a model of the atom that's not the Dalton solid sphere model, that's not the Thomson plum pudding model, that's an improvement over both of those. Well, in the end, we say that the atom consists mostly of empty space with a small, dense, positive nucleus in the middle. And then surrounding that small, dense, positively charged nucleus are the electrons that are orbiting around it in circles. Okay, this is a big deal. And what I said yesterday, I said, I consider this to be revolutionary. Okay, Thomson's model was a huge deal. It was revolutionary because it was an acknowledgement that there was something smaller than the atom. But so is this, because this takes us from just there's something smaller than the atom, but the way it moves around is all wrong, to something that looks an awful lot like our current understanding of the atom. It's not exactly our current model, but it looks an awful lot like our current model of the atom. Let's fast forward now to another guy, our fourth model of the atom, fourth of 5 models of the atom, one put forth by a guy named Niels Bohr. The Bohr model of the atom has 3 aspects that we're going to talk about here today. Now, Niels Bohr comes along and says, this whole Rutherford model of the atom, I kind of like this guy, Rutherford. Like what he did a good little experiment. Says there's a nucleus, empty space, positive nucleus, electrons orbiting around, all that stuff. Yeah, I can live with that. I like that. That seems to fit with what I believe. This whole nucleus, positive, small, dense, empty space atom, electrons orbiting around it. But Niels Bohr says, I want to go a little bit further than that. I want to take it a step further. You don't just have electrons orbiting around the nucleus wherever they want. Okay? You don't just have electrons doing whatever they want around the nucleus. Rather, we're going to take it to the next level where these electrons, although they do orbit around the nucleus in circles, they orbit around on specific levels we have very specific electron levels. And each of those levels is characterized by a specific amount of energy. It's kind of like you go to a hockey game at the Saddledome. How many people have been to the Saddledome? Everybody? At some point or another for some? You go to a hockey game at the Saddledome, and you know what? You go to watch the game, you got to sit on one level or another. You don't sit on the 2.5 level. You sit on the first level or the second level or the third level. And you know what? You like to fill in the first level first, right? Everybody wants to sit down in the good seats. That's what electrons do too, right? They got levels, but they want to go to the inner levels first. How many can you have on the first level? 2? 8 on the second level, so on. You don't need to remember those numbers for physics, by the way. You do for chemistry, not for physics. But you guys know from chemistry you can have a certain number of electrons on each level. You want to fill in those lower ones first. Okay? That's the same thing with the Saddledome, right? You want to fill in those lower levels first. You know what, guys? You go to the Saddledome, and it seems like the people on the first level, I don't know if you ever noticed this, they're the people that are just sitting there, you know, maybe ordering their hot dogs or their beer from the guy that's walking down there in the tuxedo, okay, in the special section there, the present section there. Okay, they're the people that sometimes don't even really like hockey that much. They're just kind of there for the social aspect of it. They're not really cheering that much sometimes. Okay, they're pretty quiet. The energy of those guys is, you know, maybe not so much. Okay, you go up a level, the second level, it's characterized by a different amount of energy. People are louder in the second level than they are in the first level. They're cheering more. In the third level, it's even crazier. The third level is characterized by a different energy. The electrons, same deal. Electrons exist on levels. They want to fill in the lower level first. Each level, just like each level of the Saddledome, is characterized by a specific amount of energy, a different amount of energy, right? Now, what's the second aspect of the Bohr model of the atom that separates it from the Rutherford planetary model of the atom? We call it stationary states. What does that mean? Let me do a little demonstration for you. I'm going to swing the keys around my head on the end of the lanyard. These keys represent the electron that orbit around the nucleus. My fist is the nucleus. As these electrons orbit around the nucleus, or as these keys orbit around my fist, they move in a circle, right? They're going at a constant speed. They're not speeding up, slowing down, but they are accelerating because the direction's changing. What's the type of acceleration that they experience? Do you guys remember that? It's a physics 20 thing. Circular motion. Yeah, what do we call the acceleration though? Centripetal acceleration, right? The acceleration toward the center of the circle. You guys remember that? These keys, even though the speed is constant, they accelerate. Now, remember what Rutherford said, not Rutherford, but Maxwell, way back at the beginning of Unit 4, our EMR unit, Maxwell said that every time charged particles in general accelerate, they emit EMR. They produce EMR. That's accelerating charged particles generate EMR. But these don't. These electrons, as they're orbiting around the nucleus, they should, according to Maxwell's theory, generate EMR. But they don't. I'm going to put in brackets here. They should emit EMR. I want to put Maxwell accelerating charges, just to remind you why they should emit EMR. But they don't. They seem to be exempt from the laws of electromagnetism. You know what? It's almost as if these electrons, as they orbit around the nucleus, aren't accelerating. They are, but it's almost as if they're not. In fact, it's almost as if these electrons, as they orbit around the nucleus, are stationary. They're in a stationary state. That make sense? It's as if they're stationary. Now, in the end, how do we know that they don't emit EMR as they orbit around the nucleus like that? Well, because imagine if they emitted EMR, they're giving off energy, right? As these keys give off energy, these keys lose energy themselves, right? What happens to these keys is they lose energy. Watch what happens to these keys as they lose energy. Watch. Keys lost energy. What happened to them? They spiraled into my fist, right? They spiraled into the nucleus. That's what would happen to the electrons if they gave off energy as they orbit around the nucleus. They would spiral into the nucleus. The world as we know it, matter as we know it, we wouldn't even be talking about knowing it because we wouldn't be here. Okay, matter as we know it wouldn't exist because electrons wouldn't be orbiting around the nucleus as they do. They would be spiraling in toward the nucleus all the time. Within a fraction of a second, any orbiting electron would become a part of the nucleus. And that just doesn't happen. These electrons, as they orbit around the nucleus, even though they should give off EMR, according to what Maxwell said, they don't. It's as if they're stationary, in a stationary state. Finally, the third aspect of the Bohr model of the atom talks about transitions. Electron transitions. You walk in to the Saddledome on that first level there, the main entrance to the Saddledome, and you got a seat in the third deck, the sport check zone of the Saddledome. This is where I used to go in the late 90s when I was young and single and poor, as opposed to now when I'm just poor. I'm no longer young and single. I pay $8. That's what it cost to go to a Flames game in the late 90s. $8 to buy a Sport Check Zone ticket. A movie at the time was $9. It was $1 cheaper to go to a Flames game than it was to go to a movie. I used to go to the Flames games all the time, and it was easy to get tickets. There was maybe 11,000, 12,000 people going to a game. There was 7,000 empty seats in a game. When you'd walk into that main entrance of the Saddledome, and you had that ticket for row 20 of the Sport Check Zone, way up in level 3, you knew you better have some energy here, right? You need to maybe make sure you eat your Wheaties for breakfast in the morning, or maybe have a Red Bull or a cappuccino, whatever you guys drink at Starbucks before you go up to the top deck of the Saddledome here, because it's a long way up. You got a lot of climbing to do, right? You need to absorb a lot of energy. Electrons can make transitions from low levels to high levels, from the main entrance of the Saddledome up to the third deck of the Saddledome. But when they do that, they need to absorb energy. So we're going to say electrons make transitions from low to high level. When they do that, they absorb energy. Usually the energy that they absorb in that case is EMR, but it doesn't have to be. They can absorb energy from other sources as well, but usually it would be absorbing a photon. Okay? A photon of green light strikes this electron, and that green light absorbs this energy from the photon and jumps to a higher level as a result of that. But again, it can get it from other sources as well. Yeah, I go into the Saddledome, I need to make sure I had a Red Bull before I go in there because I needed to absorb energy to go from the main entrance up to the third deck of the Saddledome, up to a higher level, because it's a hard walk up there. Now, electrons can also make transitions from high levels to low levels. This was my favorite part of going to hockey games in the late 90s and spending $8 to get there. There was 7,000 empty seats a game. You'd pay $8 and go sit in row 17 of the third deck, and the entire first period, you'd watch the first deck, you'd watch empty seats to make sure nobody sat in there, and then in the beginning of the second period, you'd go down there and take their spot, because nobody's sitting there. Electrons can make transitions from high levels to low levels as well. You know that, right, from chemistry class, you know that if there's a vacancy in that first level, hey, electrons fill it up, right? Okay, you don't want a vacancy there. If there's a vacancy in the first deck of the saddle dome, hey, what am I going to do? I'm going to go down and fill it up, right? I take that seat. Okay, when electrons make a transition from high levels to low levels, they give off energy, or they emit energy, just like I do. Okay, when I'm going from the third deck to the first deck, I let out this little shriek of glee, giving off energy, because look, I just spent $8. I'm going to sit in row 6 of the first deck. I spent $8 to get to this game. I emit energy. Electrons emit energy in the form of EMR, electromagnetic radiation, when they go from a high level to a low level. Think back to day 2 of your EMR unit, and we went through the spectrum, right? Remember radio waves, microwave? Forgot that song? Now you remember it, hopefully. If you think back, we talked about how each type of EMR was produced. We said radio waves and microwaves are produced by oscillating electric charge. Charges going back and forth. We said X-rays are produced by rapidly decelerating electrons. Gamma rays produced by nuclear decay. We said infrared, visible light, and ultraviolet were produced by, how do we say? What do we say? Transitions of electrons in the atom. That's what we're talking about right now. Transitions in the atom from high levels to low levels. That's how you get visible light, or infrared, or ultraviolet, or in the odd case, even something like an X-ray, if it's a really, really big transition. Maybe, to go with the stadium analogy for a second, instead of going from the third deck to the first deck of the saddle dome, okay, you release energy when you do that. But maybe you're in a football stadium that holds 100,000 people, and you're in the last row at the top, and you see a seat in the first row. Okay, that's a big transition down there from the last row, the highest row, to the first row. Maybe you give off an X-ray there, okay, a really, really high energy photon. But most cases, it's infrared, visible light, ultraviolet. Got it? So what do we observe when electrons make these transitions? Okay, you got a photocopy of this slide in front of you right now so that you don't have to copy it down. I want to show you these 3 diagrams and what they represent and how they're related to what we've just been talking about. First diagram, not really related at all to what we were just talking about. So why do we put that there? It's what we call a reference diagram. Okay, it's so that we can compare the other 2 diagrams that are related to what we just did to something. Okay, our reference diagram has matter at high density. Maybe it's a solid, maybe it's a liquid or a gas at high pressure or high density. Maybe it's an old style light bulb, like an incandescent light bulb, right? Not the CFL ones or the LED ones, but one of the old style light bulbs. It produces, when it's turned on, white light. It generates all the colors of the rainbow. Okay, when we turn on that light bulb, okay, we see all the colors coming down. And if we use a diffraction grating or prism to separate those colors of white light, then we get a continuous spectrum. We get all the colors of the rainbow kind of going from one to the other. That make sense? That's not a result of electron transitions. That's just the fundamental nature of a solid, liquid, or gas under high density or high pressure. Okay, it's the way it is. It's not electron transitions. Now, let's look at the second diagram, which does involve electron transitions. This time we got a hot gas, and this hot gas is under a low pressure or low density. What does it produce? Well, there's transitions that take place here from high levels to low levels. So it produces very specific frequencies of EMR. It's not producing white light. We may look at this hot gas, and we may see white light coming out of it, but really that white light doesn't consist of everything. It consists of very specific frequencies or very specific colors. When we put that apparently white light in front of a prism or diffraction grating, it splits it up again. But it's not going to split it up into the rainbow because we don't have all the colors. Rather, it's going to split it up into just the colors we have. A little bit of red, a little bit of yellow, a couple colors of green, okay, a blue, an indigo, and a violet. We get what we call a line spectrum or a line emission spectrum that shows us a photon for each different transition that's taken place. Okay, a hot gas under low pressure releases all of these photons. Before they get to this diffraction grating or prism, it looks like white light, but the diffraction grating or prism splits it up into the component colors. Okay, it's different than the first diagram we have because this gas under high pressure, or this solid or liquid, produces all the colors. This produces only specific colors corresponding to specific transitions. All right? What do we see in the third diagram here? Well, the third diagram looks remarkably like the first one, actually, except that we've got a cold gas in there. Let's take the cold gas away. Okay, it's gone for just a moment. If we take the cold gas away, then it's exactly like the first diagram, right? What do we get? Well, we got high density hot matter. It's gas maybe under high pressure, high density. We get white light. And it's not because of electron transitions. It's just because it generates white light. Generates all the colors of the rainbow. When we put that through a diffraction grating or a prism, it splits it up. So now we see this. We see the continuous spectrum. But let's introduce that cold gas. We put that cold gas in here, what happens? You got white light, but the cold gas absorbs some of the white light. There's certain photons that are in that white light that are taken by electrons so that they can jump to higher levels. So they do that. The electrons go from the first level to the third level, or the first to the fifth, or whatever the case may be. What do you got on the other side of the diffraction grating? Well, you got your continuous spectrum again, right? Not quite. You got a continuous spectrum minus a photon of red light here. Where did it go? Where did that red photon go? Why isn't it there anymore? It was a continuous spectrum. Okay? Why isn't it continuous now? Why are we missing a photon of red, a photon of yellow, a couple photons of green, a photon of blue? Where'd it go? Yeah, it got absorbed by electrons to make transitions. So you got the continuous spectrum minus whatever was taken away by the electrons as they made transitions from low levels to higher levels. That make sense? Now, I don't know what gas this is for. Hydrogen, I don't know. I don't know what it's for. It doesn't matter. Okay, but understand two things here. First of all, this emission spectrum, if you take a close look at it, this emission spectrum is the exact opposite of this absorption spectrum. Where all the photons were produced in this transition, all the photons were absorbed in this transition. What does that tell you about this hot gas as compared to this cold gas? What do you think that tells us? One's hot, one's cold? No, the picture doesn't tell me one's hot, one's cold. It kind of does, actually. It tells me it's the same gas. This spectrum is unique to this gas. Again, I don't know what gas it is, but for a different gas, you would get a different emission and a different absorption spectrum. In fact, we can not only predict, we can show what gas we have simply by looking at the spectrum. When I was in my first year university, I went to a little university called St. Francis Xavier in a little town called Antigonish, Nova Scotia. And I remember taking a physics degree. You got an office in the physics building. Okay, so I got an office that I shared with 3 other people in the physics building as a student. And it was great because it was a great place to sit and do work and to study and whatever. And there's always 3 other students there. Okay, we spent tons of time there working. Always 3 other students there in your office with you to bounce ideas off of, right? I give you guys these mini assignments and I say, yeah, talk about it, like discuss things, debate things. And we did that all the time. but because you spent so much time there, you got to know other students really, really well, and you got to know professors really, really well, and so on. I remember one professor I had, his professors at universities, especially in science, their main reason for being there is not teaching. It's research, right? Scientific research. You teach 2 classes, and then you spend the rest of your time doing research. Well, this one professor I had, his area of research was atomic spectra. He would photograph atomic spectra, and I remember touring his lab, not knowing anything about it, because I never learned about this stuff in high school, not knowing anything about atomic spectra. He was telling us what he did, and I remember thinking, boy, oh boy, oh boy, if I had to do that every day for the rest of my life, I think I'd go insane. Photograph atomic spectra, because why? Like, sometimes it's good to know things for the sake of knowing things, but doing this every day for your entire life, that seems like a bit much, when there's no practical application for this. It wasn't until later on that I realized, wait a second, when I learned about this, I realized there are lots of practical applications for this. For instance, maybe you're an astronomer. Okay, maybe you've just discovered a star out there in space that nobody else has ever discovered before. Nobody else has ever seen it for whatever reason, just appeared, and hey, you're the first guy to see it, or the first girl to see it. And you look at it and say, that's neat. I wish I knew something about that star. So you take a little diffraction grating or a prism or a spectrometer, and you observe this star. You shine the light from the star through this spectrometer. What does it do? It splits it up, produces a spectrum. You see this. You say, wait a second. Hey, that professor I had in my 2nd and 3rd year university, I saw the picture of that before in a paper that he published, a scientific paper that he published, had that exact picture in there. That star that I just observed must have that unknown gas in there. It must have that in there. So I've just determined the composition of the star by comparing the spectrum that I've observed from that star with known spectra that guys like my professor photographed, studied and photographed. Does that make sense? Let me give an example, and then it's break time, okay? We got 3 spectra up on the board, 3 spectra that were photographed by somebody. These are in black and white. These appeared on an actual diploma exam years ago before they introduced color. Now, if you saw this question on a diploma exam, it would be in color. Now, don't get too excited. The diploma exam is 50 questions, and usually there's about 1 page that has a little bit of color on it. And oftentimes that color seems inconsequential to the question. Why they do it on 1 page for an inconsequential question, I'm not sure. But if they give you one of these questions, it'll probably be in color, and it'll be helpful to have it in color. These lines right here will be colored lines. Notice that hydrogen, helium, and sodium are all different, right? All different spectra. We would expect that. Each element has its own unique spectrum. These are photographed by maybe my professor, maybe by somebody else. Now we get an unknown gas mixture spectrum. Okay, we're looking at this through a spectrometer, and we see this. We want to identify what it is. What's its composition? We compare it. What do you think it is? By comparing it against the known spectra up here, 1, 2, 3, what do you think the unknown gas spectrum is? John? First and third, hydrogen and sodium. Okay, why do you say that? Good. Here's what's important. Okay, it's not important to say, oh, look, that's in sodium. Okay, we don't do that. We don't want to go this way. We don't want to say, oh, this is in sodium, therefore sodium must be there. We want to say, every line in sodium is present in the unknown gas. Every line in hydrogen is present in the unknown gas. Look, this one is present in the unknown gas, but this one isn't. We need all the lines in the gas in the known spectrum to be present in the unknown gas for that to be there, for us to say that that's there. So therefore, we're going to say that this is going to be a combination of, as John said a second ago, hydrogen and sodium, right? You just determined the composition of a star. How easy is that? Right? Make sense, guys? What you see now in front of you is what we call an electron level diagram. This shows us a number of things, including the different levels that the electrons can exist on. Okay, this is the ground state down here. We say it's the first level. The nucleus would be down here somewhere. And then the ground state would be the first level above the nucleus. Then we got the second level, then the third level, then the fourth level, fifth level, sixth level, and so on and so on and so on, until we get to the infinite level. The infinite level is where the electron has actually left the atom. It's become ionized. The electron is no longer a part of the atom. Notice a couple of things. First of all, that these lines are not evenly spaced. These levels are not evenly spaced apart. Okay, the first level to the second level is a certain distance apart, and then we go from the second to the third. They keep getting closer and closer and closer. I'm not suggesting here that there's only 6 levels. Okay, there could be 100 levels, but they keep getting closer and closer and closer, and at some point I just can't draw them closer and closer and closer. Okay, so first thing is, notice that they are different distances apart. They keep getting closer together the further they get away from the nucleus. Also notice that the energies labeled here are all negatives, which seems a little bit odd. All the way up to 0. They're negatives, but they keep getting smaller values until they get up to 0. 0 energy is when this electron has become ionized, when it's gone from the atom. It's no longer in the atom. It's in the infinite level. It's left the atom. It's become ionized. But why is it negative below that? Well, let me give you another analogy to help you to understand this, hopefully. What would you say my gravitational potential energy is right now? As I stand on the surface of the Earth right now, what's my gravitational potential energy? Not a trick question. What is my gravitational potential energy? 0. Good. Relative to the ground, it's 0. Now, I can define potential energy relative to whatever I want, but I usually define it relative to the ground, which means my potential energy right now is 0, right? If I climb a ladder, my potential energy becomes 100 joules, 1,000 joules, 10,000 joules. Depends on how high I climb the ladder, right? What if I dig a hole? But I still define my potential energy relative to right here, the ground. If I dig a hole, then as I climb down the ladder into that hole, my potential energy becomes negative, right? In fact, the further down I go into that hole, the more negative it becomes. The closer I get to the core of the Earth, the more negative my potential energy becomes. This is the surface of the Earth. When the electron has left the atom, it's become ionized. That's the point where we're going to define our energy as 0, our potential energy as 0. But as these electrons dig a hole and go down into the Earth, closer to the core of the Earth, or closer to the nucleus, their potential energy becomes negative. It becomes a bigger number, but negative value. Does that make some sense? Yeah? Notice one final thing on this. This diagram shows a whole bunch of transitions that can take place. A whole bunch of transitions that can take place to level 1, level 2, level 3, and so on. We have names for those series. Okay, names for every transition that goes to level 1 and to level 2. You don't need to know those names. Okay, that's not important. Okay, if they're ever mentioned on a test, the diagram, the labeled diagram, will be given to you. So don't panic about that. All right. Let's take a look at the first example that we have on this handout that I gave you a few minutes ago. First question says, using the above diagram, determine how much energy is emitted in the second line in the Balmer series. Second line in the Balmer series. So let's go back to our picture. The Balmer series is right here. Here's the second line in the Balmer series. Look at the transition that's taken place in the second line of the Balmer series. It's going from level 4 to level 2. It's going from 0.85 to negative 3.4. Want to solve this? Let's say delta E is equal to EF minus EI. The change in energy, the energy involved in the transition, is final minus initial energy. My final energy here is negative 3.4 electron volts. My initial energy is negative 0.85 electron volts. So it's negative 3.4 minus negative, what did I say that was? 0.85. I do the math there, it works out to be negative 2.55 electron volts. So there would be a photon given off here, a photon of EMR given off here. That photon would have an energy equal to 2.55 electron volts. It's a negative value because negative means given off. If it was to be absorbed, so electrons jump to a higher level, then we would say that it would be a positive value, positive 2.55. Let's try another one. This one says using the diagram, determine the ionization energy for an electron on the first level of the hydrogen atom. Hey, what's that mean? Ionization energy. What does it mean to ionize some? Yep. Sorry? Yeah, for the electron to leave the atom. So how much energy is required to get the electron from here to here? Well, we're going to do it the same way as we just did the last question, right? We're going to say delta E is equal to EF minus EI, but this time we're going up. So the final energy is the higher level. The energy of the final is 0 because it's the infinite level. The initial energy was negative 13.6. 0 minus negative 13.6 gives me 13.6. Notice it's a positive because energy was absorbed in that case. It's not given off. Finally, one more question. This one's in your textbook. How much energy must a hydrogen atom absorb for its electron to go from the ground state to the third level? From the ground state to the third level. Let's go back to my picture again. From the ground state to the third level. Negative 13.6, negative 1.51. We're going to say delta E is equal to EF minus EI. The final energy was negative 1.51, and the initial energy was negative 13.6. And we do the math there, I think it works out to be positive 12.09 electron volts. Again, positive value, we absorbed. Make sense? Let's go back here just for a second. In order to go from 1 to 2, we need to absorb, what is that going to be, 10.2? In order to go from 1 to 3, we need to absorb, what do we say, 12.09? And so on. The number keeps getting bigger, right? What if there was some source of energy that was maybe 11.3 electron volts? And it struck an electron. And the electron said, hey, look, I got some energy. I can jump to a higher level. Where would it go if 11.3 electron volts was available to be absorbed? Where would it go? Cal's your hand up there? No? It would go to the second level. Why would it not go to the third? Didn't get enough energy, right? If it goes to the second level, understand this. When it goes to the second level, it wouldn't absorb 11.3. It would absorb 10.2. The other 1.1 would go somewhere. It has to have this exact amount to go to the second level. But if more is available to it, then it can still go to the second level and just say, hey, you use the rest of the energy. I don't need it. Right? Is that good, guys? All right, here's your homework for tonight. In addition to the questions that you had last night that we didn't check over today, I want you to do the questions on page 775, please. Notice one small thing with this, guys. These questions have both of the answers in joules. You can use the diagram that I gave you for hydrogen, okay, keeping in mind that you could do this for other elements as well, just the diagram would be different, that's all. Different numbers on the diagram if it was lithium or sodium. Okay? You can use this diagram for these questions. But notice my numbers are in electron volts. There's a version of this in your textbook that's in joules. Okay, I don't care which one you use, electron volts or joules, but they want the answers in joules, so you either use their chart or use my chart and then convert it to joules in the end. Does that make sense? And they both give you the same thing, just slightly different way of expressing it, that's all. All right, let's get to work on those and finish them up for tomorrow, please.